So we're going to learn about how to start up faster, getting it actually to being productive earlier in the process, completing faster. That's usually the one we're thinking about, getting a faster response, and running with a smaller footprint. These optimizations are often exclusive, so you will get fast but big, or big or small but slow. So if you're lucky, you can get more than one. But a warning about this, and that is that often we do our programming and then say, okay, it's done. And then we find out later, oh, we need to optimize this, it's too slow. And I caution you, don't optimize unless you absolutely need to. Usually you end up making things worse. You introduce new bugs. Most of the stuff we're going to talk about is going to be things that will not introduce new bugs, just their minor tweaks. But it is possible and a little dangerous if you're optimizing that you can make things go bad. So it's usually the final step after you're done. I recommend not guessing where it's slow. Run a profiler to actually find out where it is slow. Almost every time where I've had to optimize a program, I guessed the wrong thing, that there was something else that was actually slow and I didn't realize it. There are cases where you may have to do a design change to get it to go faster, and these tend to be algorithmic things, but most of the time this is not the problem. You can usually get enough tweaking of rather small things to get the performance that we need, but we'll talk about that as well. What I'm going to show you is some antisocial stuff. You'll get people to hate you. They'll wonder what's wrong with you if you're programming this way, but they are ways to be able to modify your code. It'll look goofy, but it will improve your performance. So this talk we're going to go through is we're going to talk about some small optimizations. Then we're going to talk about, and that's just general performance. And then we're going to talk about your startup optimization, so you actually get the thing initialized and actually running faster or sooner. And then we're going to talk about profiling, how to do that. We're going to talk about some general optimizations that aren't related to Perl, but are related to operating system, file system, those type of things that will apply to any language. And then we're going to talk about reducing your memory footprint, different strategies you can have to make your program actually run smaller. And then we're going to summarize everything. So this first part is the small optimizations. Comes from a talk I did in 2018 called Perl Optimization Tidbits. You can actually look this up and watch it on YouTube. These are equivalent minor syntactic choices. So things that, where you do things, that you'll get right what this is in just a second. But they can make a difference, and some a significant difference. So the first one is don't use post-decrement or post-increment, use pre-increment. Put your plus plus on the other side. That's a little bit faster to do it that way. Same with the decrement, put the minus minus at the beginning. The prefix form is faster. If you are using regular expressions, like in a match or a substitute, don't use suffix modifiers or match modifiers that are not being used. So get rid of the I if you don't need to ignore case. If you're not doing if you don't need to do global, you're going to be replacing one. Don't use the G. You don't need it. MSX, you don't need to use those most of the time. So if you know you're not needing them, don't use them. In regular expressions, avoid dot star if you can afford to. If you don't need a new list, you can use for each instead of map. For each is actually faster. We also have the inside out for each, or sometimes called the suffix form, where you put the for each at the end of the line, and then you have a single statement that it loops over. This is actually faster. And the reason why it's faster is because we don't introduce a new scope. Every time you have the curly braces, it has to go create a scope, and that takes time. The same thing with an if. You can use an if as a statement modifier. And I don't always like the way these look. Sometimes these are awkward to do the suffix modifier on these, but it actually can improve your performance because of the scope. So in general, you want to avoid creating scope if you don't need it. Use the low precedence form of and instead of the double ampersand. That's actually faster. Same with the or. Use the low precedence or instead of the double vertical bars. And if you can construct your if statement or your conditional to be to use or instead of an and, it will actually be faster. Double quoted strings are faster than single quoted strings. I would have thought it was the other way, but in testing, it turns out that double quoted is actually faster. If you demark your variables inside of a double quoted string, it's better to do so with the curly braces than to just let Perl figure it out, which is the variable. If you have a choice, a constant string on the left side of a concatenation is actually faster than having it on the right side. And a lot of times you don't have choice about some of these things, but if you do, this is something that's actually faster. And a lot of people are going to hate this. Don't use my. My takes time. And if you do need scoping, prefer local over my. It's faster. If you can use direct access of a scalar parameter, that will save time as well. If you use shift to pull off a parameter, it's faster than copying the parameters from the @ array. But using direct access is even faster. Don't use a return statement. Just let the last thing evaluated be the return value of your subroutine. That will work even if it's an array or a hash. If we have an if-else statement, you can use a do form for that. That will actually be faster than the if-else. Or you can use a ternary operator, which is even faster. And I know some of these things are going to make your code look awful. If you have print statements, combine everything into one. Don't do print, 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 print. Avoid the concatenation operator in print statements. Print handles a list better than concatenation. Don't defeat buffering. So your $vertical bar or your output auto flush, make sure that that is 0. It's 0 by default, so normally you don't have to worry about it. But you see a lot of code that has that turned off so you can see immediate feedback. You don't want to defeat that. Let buffering work. It'll save you time. In general, arrays are faster than hashes if you're visiting each value. However, if you're searching an entire huge array for a single value, then it's faster to get it out of a hash. If you're worried about where, if it's a small array, can I scan it? Or should I use a hash? It's usually about 100 elements is about the break point where it's about the same. Whereas if it's larger, you'll want to use a hash. If it's smaller, you can use an array. The interesting thing about that is this is generally true for other languages, not just Perl. Avoid using multiple indirections. Instead, use a temporary variable to get at the piece you want. And even worse is avoid setting values. This is even slower if you're using multiple indirections. So I should have said this up front. The tests on this were done on Perl. Not all were done, all these tests were done on the latest version of Perl. They were done on Perl 16, 5.16, 5.22, and then 5.32 was the last one. But not all of them were done with all of them. That is kind of a floating range for some of these. Turn off warnings. I like the Perl -X. That seems to be more effective. When you say use warnings and no warnings inside the code, that actually isn't as effective. You're not going to get the benefit of having them off in terms of the speed performance. The Perl -X is probably the best thing. But you can do the same thing with the W variable. Use split instead of match. And slurp. So you slurp, if you're not familiar with slurping is basically reading in an entire file in one operation. And so there's a number of different ways you can do this. One way is you'd undefine the input record separator, which is $/, and then you just read into a scalar variable. It puts the entire file in a string. And then what you do is you do whatever operations you need to on that string. So if you do a match or a substitute, use the global operator. You might also need to use the M and the S modifiers too to get exactly what you want. I should mention that I have a friend who had to process log files. They're about a gigabyte or two. And he was reading a record at a time, and it was taking about an hour to process these log files. And so he switched to slurping, and it ended up taking about 2 minutes. There's a tremendous hit you get by going out to the disk to read. So that's why slurping has a big advantage. But be aware that it will consume more memory. So you have to have the memory to be able to pull this off. If you're counting instances or want to see if a character exists, it's faster to do it with a TR than with an S. There's some really great things about regular expressions, but the downside to the regular expression engine is that it's very general. It's supposed to basically be able to work with any sort of parameters you give it, whereas TR is very specialized. And that's why TR will be faster for a lot of things. Sorting is something that can be very slow. So for example, here we're sorting and and the -M means we're getting the last modification time for a file. So we're comparing two files, or we're sorting files, and the comparison we want to do is on the age of the file, when it was last modified, and sort them essentially in modification order. The problem with this is that every time we do a comparison, we're going to be doing 2 of those calls to get the age of those 2 files. And just we'll be calling it multiple times for the same value, the same files. That's a bad idea. So what we can do is we can optimize that. And one of the ways is with a Schwartzian transform. Some of you may be familiar with this, named after Randall Schwartz. It has a map, sort, map form to it. Here's an example of doing that same thing, sorting files by their last modification date. So the very bottom map that you see there is the first one that executes. It takes the list of files and it adds the modification date to the array. And then it goes and it sorts that array based on element 1, which will be the modification date. And then that passes that to the last map, the top one, which then just keeps element 0, which will be the file name. There are some tweaks on this. There's one that's similar called the Orcish maneuver. This will be faster. In some cases, it's faster if the list contains duplicates. It's simpler than the Schwartzian transform. It's almost as fast. Basically, you're taking a cache and storing the value in that, sorting by the value in the cache rather than building the array, a new array, and then stripping it. There's another version that's a little bit faster, and it's called the Gutman-Rossler transform. This is a tweak on the Schwartzian transform. You see it has the map sort map form to it, but instead of the first one tacking on the value that you want to sort on, you're actually creating a string that has the date in a sortable order in the string, and then you're chopping that off at the end. So this will work in some instances. There's some other cases where this does not help you at all. The reason why these particular optimizations can make a difference is because if the way that you calculate the sort order is expensive, you want to be able to cache that and reuse that and only calculate that for each value in the array once, not have to calculate it each time you're doing a comparison. So the Gutman-Rossler transform is faster than the Schwartzian transform, but it's harder to code. It's less readable, and you can't get it to work for everything, but for some things it will work well. Memoize is a function. It's actually a module. You can say use memoize, and then what you do is you tell it the name of a function. And what it does is every time you call that function, it will cache the value based on the arguments that are passed to it. And so if those same arguments are passed, it won't calculate that value in the function. It'll just return the value that it did before. So it's just a caching system. It works really well if the values are consistent. So every time you call that slow function, if it always returns the same value given a set of inputs, then it will work for you. But if the values can vary, it won't work. If your slow function is actually fast, it won't make any difference. And it does take a lot of memory, so you have to be careful about that. If you have a database, connecting to a database can be slow, and it may tie up a license. So if you can keep a database connection open, that can help your performance. A lot of times we have these commercial databases that have limited number of licenses, like you have 5 licenses for your company, and every time you run it, ties one up until it's done. That can be a problem if you have multiple things that need to connect to the database. So beware, that's a problem. But if you only have to connect once and then do all your stuff, and then when you can disconnect when you're done, that can be faster than connecting every time. If you're going to only conditionally need to use a module, you can put it in like if it's inside an if statement, that the only place you're going to use that module, you can put a require in that if statement inside that block, so you don't have to load that module if you're not using it. Keep in mind that this is there's compile time versus runtime issues going on here, so be aware that it'll be only compiled at runtime. You don't want to load unneeded modules. That can actually slow you down quite a bit. And you have to be careful because there are some modules that will load other modules that will load yet other modules. And so you may end up loading a lot more than you're aware of. The key is you just want to load the pieces that you need. So here's an example where we have IO util. We just want to use the slurp function. And so what we do is we say, quote word slurp, so it just loads that portion. And then we can call slurp directly, or if we just use empty parentheses, after in the use statement, then we need to give the full path to the slurp function. Either way works. If we're using the stat function on a file repeatedly, remember you can use the underscore variable to pull the previous stat values. Underscore is cached. It is the only Perl variable that does not have a sigil. There's no $sign or anything like that in front of it. If you're running on a web server, should be using mod Perl. If you aren't, you probably may not be aware that that's an option. But mod Perl will improve your performance on a web server significantly. Don't use signatures. If you're not aware of what signatures are, it's where it looks a lot like other languages. So you give your parameters in parentheses where you define your subroutine. The problem is this takes extra time, so don't do that. One interesting thing is that you can call a subroutine. If you have a subroutine you call with no parameters, it's actually faster to use the ampersand on that rather than putting parentheses after it or both. It's about a 5% gain. If your match operation is going to be only used once, you're not going to have a variable inside that regular expression. You can use the compile once modifier. That may or may not make much difference. However, never use the return values from the internal part of the regular expression engine. $, $, backtick, and $apostrophe. If you use any one of these anywhere in your program, it slows down the entire program. So don't use any of them. Don't think you can get away with it one place because it'll affect every time you use a regular expression. If you have hardware that does not have a built-in floating point processor, you can say use integer as a pragma, and what it'll do is it will not do, and if you're not doing negative numbers or floating point numbers, you might be able to get away with this and with use integer, because what it does is it says, oh, I'm not using floating points, so it won't load that stuff. It won't try to calculate things as floating point numbers. It'll do it only as integers. That may make a big difference. Avoid subroutine calls by using inline code if you can. I know it'll make your stuff look like spaghetti code, but that might be another option. For example, if you have a for each loop and you have a subroutine call inside of that, you can minimize the subroutine call if you can push that loop down inside of that subroutine. Don't use code references. So here we're actually creating an anonymous subroutine. Those actually are a little bit expensive. Don't do that. Don't use data dumper on large structures. Don't use keys or values on large hashes. You might want to try different versions of Perl. There are some older versions that are better at some things, and some new ones are better optimized. So if you're having a particular problem, you might want to try different versions to see if that helps. And avoid versions of Perl with compiled threading or debugging, unless you know that you actually need those. Look at minimizing calls to any of the functions that take lists or generate lists. Things like grep, map, sort, chop, chomp, keys, values. There's a whole bunch of them. Minimize the use of your regular expressions, but especially anything with a G, global suffix modifier. So here's an example. grep will always run through the entire list that you give it. A for each can short circuit and drop out early. So if you're looking for something and you only know there's only one of them, so we're looking for the line that says total in it out of the items list, we can grab that with a grep. But we can also get it sooner on average if we just do a dropout of a for each. If it's still slow, we know there's a section of code that's a problem. We can actually replace that with C code using inline C or XS. Now let's talk about optimizing our startup time. How fast did it actually is it getting to doing real work? Don't use moose, moo, mo, or any object-oriented stuff. I've worked a number of places that have banned moose and its derivatives just because of the startup penalty. It's a little disconcerting when you're every time you have to test, you have to wait 30 seconds or a minute before you can have any results, just because it starts up. There's an old thing that I don't think is ever used much. It's called core dump. What it does is it creates, you put this call somewhere in your code after your initialization is complete, and what will happen is it'll create a core dump. It'll terminate your Perl script, create this dump file, and then you can undump that to start it running. However, it doesn't work on all operating systems. Some people claim it never works. I actually worked at a place that did use this. They were creating this huge internal data structure, and it took quite a while to get that to be initialized so they could actually do some processing. And so they ran a dump call on that once it was done initializing, and then you essentially undump it, and it would start running at the point where it left off. So it was actually really fast to start up that way because we used that dump. You can look at doing a Perl compiler. There are some out there. There's one called rPerl or restricted Perl, but it's a limited subset of Perl. It might not work for you. Depends what you need. You can go to rperl.org, but it advertise itself as being faster than Perl. Don't use Catalyst. I can't speak for Dancer. I've not had an opportunity to use Dancer, but Catalyst can be quite slow. CGI EX is actually quite fast and was developed specifically for speed. So if you need that type of web framework, this is one that can work for you. So if your startup is still slow, you may have a hidden call to Moose or one of its derivatives, or maybe you're just loading too many modules. There's a place you can go on Perl.com to actually see more details on this kind of stuff. If you just Google a timely start.html, you'll get to this page. Let's talk about profiling. Profiling is the process of tracking a running script to identify how much time is spent on various parts of the code. Currently, the gold standard is NYT-Prof. It's the best profiler out there. However, if you're running on some old Perl, you might not have it available to you. The way you run it, and all the just about all the profilers, you use the debug option on the command line, -D, and then you give the name of the profiler. So here would be NYT-Prof, and then you give it the name of your script with whatever arguments you want to pass to it. And what it does is it generates essentially a log that then has to be analyzed. It doesn't want to go and do the analysis at the time because it'll take a lot of time and it doesn't have time. So for NYT-Prof, there's a number of different ways you can do it. One of the more popular ones is to use the post-processor NYT-Prof HTML, which will process that, essentially that profiling log and create an HTML view of that. It'll create a directory and an index.html with a whole bunch of other web files in your local directory. The - open option will open the browser, whatever your default browser is, with that HTML file when it's done processing. And it will be very graphical. Part of it looks like this, where it gives you a line of code. It says how long it spent on that line, how many times that line was called. So keep in mind that every profiler has to have some sort of post-process analyzer to be able to give you the information that you're interested in. Although NYT-Prof is really good, it does have some limitations. One of the things I ran into is that it tends to attribute too much time to the last statement in a loop. It's putting the stuff that's at the end of a loop that wraps things up, like incrementing the variable. There may be some variable scope issues that it's dropping off. Anyway, the problem is, so if you're trying to test something, you may want to put some other no-op type stuff below the bottom line in the loop, so you can actually see how much time is taken up by that one and not the overhead of the loop. It is not thread safe. It's not reliable on VMs, and it's inconsistent on SMP systems. I know there's a problem right now because a lot of the development that takes place in the industry is happening on VMs. So in that case, what you do is you need to run it multiple times. And hopefully you don't have, hopefully you'll get some consistent numbers on that. As far as profilers that are out there are a lot of specialized ones, like ones for Apache or for DBIX. There's some of these in this list are old and maybe the only one available on your system. For example, dprof is no longer distributed with the default Perl distribution, but it's there in some older ones. It does not do line-based analysis. It only does subroutine analysis. So you get the total time in a subroutine, not the total time in a line. But if you don't have NYT-Prof, this might be the only thing that is available to you. I know when I worked for Wells Fargo on a contract, they would not allow me to install anything on their servers, which I don't blame them. It's a bank and you don't want to get in trouble with that kind of thing. And so I was very limited as to what kind of stuff I could do on their servers. So whatever was the default, whatever was there was the only thing available to me. So sometimes you have that kind of situation. Now we're going to talk about some general optimization, things that are not specific to Perl, things like the I/O, the file system, some algorithmic stuff, and some miscellaneous. So the file system, if you have symbolic links, those actually take time because it has to open the symbolic link, look and see where it points to, and then go and follow that, and then open that. And you especially don't want to have chains of symbolic links. A symlink point to another symlink, which points to another symlink. Those will slow things down. Bind mounts are faster than symbolic links, but bind mounts can be a problem if you have a lot of them. So just be aware you probably don't want to do thousands of bind mounts. And the primary problem is when you unmount a bunch of bind mounts, it's just slow. I did a test case where I had 20,000 bind mounts on a system, and the projected unmount time for an orderly reboot was 8 hours. However, the cool thing is I could just say, cycle power on it, and it reboots instantly. But the unmounting of bind mounts can be slow if you have a lot of them. So also bind mounts have an advantage that they can work on files and on directories. Whereas if we use hard links are fast, because they're just essentially yet another directory entry for a file. They point to the inode for the file, so they're just as fast as the original file entry. But they have a problem that they only work on files and they do not work on directories, only files, and they cannot span file systems. So they have to be on the same device. And that's because they're pointing to an inode. Another possible improvement is switch to solid-state drives. Downside with SSDs is that their performance degrades when they start approaching capacity. If you have hard disks, you can get better performance with a hard disk by using more but smaller drives. More spindles will give you faster access. We talked about slurping. You can slurp into an array, or you can slurp into a scalar. Just about every language has a way to do slurping. Many years ago, I worked on a contract with the government. It was for a flight database where we had digital map data provided by the Defense Mapping Agency, and it came on a mag tape, the big reels. And to read that off, the original person that wrote it so because we were running on a VAX, we would read off a record, and then flip the big endian to little endian, and then save it. And so it was actually much faster. I changed it, and it would take about an hour to read the whole tape with all that data and flip those bytes. So instead, I changed it to read the entire tape, and then as we were actually running to do the processing of the data later, they would flip the bytes. It turns out the flipping at that time takes almost no time at all. The real time saving was the reading of the tape. And we got it down from an hour down to about 2 minutes. So it was a form of slurping. So that's always an approach you can look at. Reduce any I/O that you have. Turn off logging. Turn off debugging. If you can build an output into a buffer, and then flush that all at the end. Do all your I/O at once. If your network data I/O disk access is slower than your script, then there's nothing you can do inside your script to improve that performance. You have to fix your I/O problem, your network, whatever it is, first. Let's talk about algorithmic solutions. These are defined generally as big O. We have big O notation, and this is concerned about what is the worst case as the data size increases. And so the notation is O1 or ON, ON times log n. It all depends on how the data has a relationship to each other. So the complexity grows. The real problem we have is when complexity grows, when the next piece of data added makes the problem much bigger. And usually the problem is that that particular new element has a relationship to the other data in the set. It has a relationship because it needs to somehow be connected with the other ones. It needs to be in a certain order, something along these lines. So let me give an example of something that's the most simple, an O1. This is selecting for example, selecting a random element of an array. It's a simple, single operation. Adding another element doesn't add much to the complexity of it, and it doesn't decrease the performance to add another element. So ON would be where we're printing the elements of an array. We have a simple linear adding one element doesn't add much to it. And so and there's little relationship to the other elements. A linear search of elements in a sorted array is similar, ON. Adding an element doesn't add much to it. But we can reduce that by doing a binary search. So we have, we're essentially, it's a complex solution, but all we're essentially doing is dividing and conquering. And so it comes down to a log n rather than an n. When we get to sorting, it starts getting really messy. A bubble sort that everybody's familiar with, essentially you have to scan the list every time to make sure everything's in order, things bubble up to the right position. But the problem is, when you add an element, it adds an entire scan to the list on average. So that can be expensive. Doing a quick sort is more efficient, but it is complex, but it gives us an n times log n, which will be less than the n squared. And there's all sorts of sorts that are on this order of complexity. And so the idea here is that we want to improve our algorithmic solution so that we're taking this complexity and reducing it so we have less things that we have to touch. Under miscellaneous things, we can pre-allocate memory. It's slow to ask the operating system for memory, but it's fast to use memory you already have. So if you need to go get a little tiny piece of memory every once in a while, like for example, we had a thing where we were creating a graphical database, and we needed to get a vertex, so an X, Y, and a Z. So we'd allocate memory for those, and we had to do that 3 times to make a polygon, and we're doing that millions of times. That's slow because you're going out to the operating system for each one of those. So what we did is we pre-allocated, we created a big array right up front, and then immediately deallocated it. That put it in our local memory cache, and then we could go and use that. And so that was actually very fast. That probably improved our speed by about 50%. You can reuse variables. If you have bounds checking, some languages have bounds checking, you can turn that off. You can always throw more hardware at it. The nice thing about throwing hardware at it is you don't have to rewrite anything, and it might be good enough. You could try a different operating system. For example, Red Hat 5.2 needed a patch to fix a speed problem with Perl. And if you have that situation, going to a different operating system might actually help. Reducing our memory footprint. Most of the time, a smaller memory footprint means a slower program, but not always. And is it important to you to have a smaller footprint? One way you can have a smaller footprint is use arrays instead of hashes. Arrays take up 3 to 4 times less than a hash does. You can use strings instead of arrays, because strings take about half as much as arrays. You can use something like dbm open, dbm close, tie or untie to keep a hash out of RAM and just on the disk. So you can have a huge hash, but it only exists on the disk. I have 50 minutes, right? I've got 10:44, so I've got 5 minutes. Okay, so dbm and dbm close are kind of discouraged right now. They encourage you to use tie and untie, but dbm open is still available. It's essentially a database format on disk for hashes, and these can actually take 2 to 30 times less memory as hashes. So an example is you'd say dbm open, give it the name of a hash, and then a name of a database. You can make that up. It'll create the database if it doesn't exist. And then when you work on that hash, it will keep that information on the disk. And then you do a dbm close essentially to save that. That can save you a lot of time. Now, dbm has a lot of different formats or different versions of dbm, so it depends on what operating system you have as to what the file format. So you can't just copy a dbm file over from somewhere. and use it somewhere else if it's a different operating system. So just be aware that that's a potential problem. Don't use the do, because that actually loads that script into memory. That'll actually make it bigger. But if you use backticks, it loads it as a separate process. So it doesn't take your memory space from in your current script. Turn off warnings. Don't slurp. If you have a database, let it do the work. Don't read everything from the database and then process it. Just read a record at a time and process that record, then get the next record. The way you can check your memory footprint is with PS, PMEM, TOP, or the GTOP module. Here's an example of how to use it. So using these ideas, some or all, or just a few of them, can make significant performance improvements in your code. However, if you use these, be aware that people will wonder what's wrong with you. And you're probably breaking some standards within the company, some best practices. So you have to be careful of that. So use it only as needed and be sure to comment if you do so people know why you're doing that. Every once in a while, I'll run into somebody who's doing something to be efficient, but it doesn't say that it's doing this because it's efficient. It's assuming that I'm getting it, and I don't always get that. So it's a good idea to always comment those. Specific environments may need unique optimizations. There's a really good document, perlapache.org. It's for performance tuning with Apache, but it also would apply to some other applications. So it's a good place to look. Although it says it here in the path 1.0, you can go to 2.0. If you go to 2.0, there isn't anything. So this is where it is. Perl.apache.org, docs 1.0, guide performance.html. Any questions? Yes. Okay, which slide was it? This one? Okay. For this particular example, a join would have probably been a good idea. I'm not sure if join would have been faster though, because it'd be doing the same thing in this instance. In fact, in real life, I probably would have used a join. Yeah, so some of these types of issues, it turns out it may be faster, it may not. And so I would, if I was really looking for performance on, is a join going to be faster than a string concatenate and this sort of thing, I would probably run it through NYTprof, a test case, and see if it actually does work better. Okay, last question. $60? 1.6? Okay, we're on, that's 16. This one. Yeah, so the question is, let me state this, make sure I understand. The shifting is faster than doing a my with your variables equals the at underscore. Yeah, it's actually, it surprised me, but Shift is actually faster. And I think the reason probably is that it's the variable overhead of doing a copy. Yeah, but that's just a guess. Okay, but yeah, so Shift surprised me. I used to discourage Shift because I thought, oh, Shift is another call over extra overhead, but it turns out it's actually faster. If any of you. Okay. Yeah, so let me make sure because I'm not sure everybody could hear. The advantage with Shift is that you're getting a direct access to the variable. You're getting the direct access to the value, whereas the copy has to rebuild a structure. Yeah, it has to move around. Okay, if anybody else has questions, you're welcome to come up to me afterward and talk. Thank you very much.